So in today's lesson, we're going to be looking at what are called ordered selections. This is where we have a bunch of objects and we're selecting them in a specific order, and that order matters. So as you can see in this example here, the first example, we're going to rearrange the letters of the word maths, and it matters which letters we choose first, which letter we choose second, and so on. In a later lesson, we're going to look at what are called unordered selections, where the order that we select them doesn't matter. It's just the selection that we make is what's important. Today, though, as I said, ordered selections, the order matters. So with the word maths, if we want to rearrange the letters into other words, and here when we say word, it doesn't have to be a sensical word, it doesn't actually have to be a word in the dictionary, it's just, when we say word, it's just made up of letters. So if we want to rearrange the letters of the word maths, then the way we're going to do it is we're going to treat these problems as if they were created of a grid. So we've got 5 letters here. We're going to have a grid with 5 pieces. And basically what we're going to do is we're going to take those 5 letters and imagine we're chucking them in a hypothetical bag, and we're going to shake the bag around, select a letter, and pop it somewhere on that grid. And then we'll shake the bag again, select one of the remaining letters, chuck it somewhere else on the grid. Okay, and we'll keep doing that until we end up with the grid full. In this case, we've put all 5 letters down. So here you can see the first letter I pulled out of the bag. So I've shaken the bag, pulled the letter out, was the letter T, and I've decided to put it on the 3rd spot on the grid. There's only 4 spots on the grid left now for me to put the 4 remaining letters. And the second letter is A, and I've decided to put it in the 2nd spot. Then I've shaken the bag again, I've pulled out the letter S, and I've put it in the last spot. Same with H and M. Until I've got no spots remaining in the grid, I've now chosen all 5 letters. And the number of ways I could have done that, as we've said for the first choice, was that there was 5 spots, then 4, then 3, then 2, then 1. And we've seen by the fundamental counting principle, I can just multiply those results together, and we've come up with a new compact way of writing that as 5 factorial, and that's 120 ways. Now there are essentially 2 ways that I can order selections. I can either allow repetition or not allow repetition. Now if I allow repetition, in this case I'm saying if I want to select R letters from N distinct letters, then there are N to the power of R ways of doing that. And the reason that that's true if I have repetition is that I have N choices. So I've got a bag filled with N letters and I shake it up. I can pick any of the N letters out and pop it down on the grid of R spaces. But with repetition, that means essentially I put the letter back in, so I record it, and then I put the letter back in and shake it up, and I've got still N letters left in the bag. So every time I make a selection, those R times to fill in the grid, I've still got N choices. So N times N times N times N. So in this case, it's not N factorial, it's N to the power of R. Here's an example of such a case. And this is an example that's not super simple. We actually have to do some work, but it's still using this definition. So here we're saying that we've got 6-digit numbers, and that we want we want to know how many of those 6-digit numbers contain at least 1 7. Now with this problem, and many problems like this, when you see the word at least, generally it's easier to attack the opposite problem, where there's no 7s in this case, which would mean that out of the 10 possible digits, remember we've got a 0 as well, we've taken 7 out, so there's only 9 digits that we could choose, and we want to do it 6 times. So we're allowing repetition here, so it's 9 to the power of 6 with no 7s. And then we're going to subtract that from the total number of cases, which has 10 digits in it, because it is allowed 7s in that case. That's 10 to the power of 6, and when we do that, we get 468,559. The other possibility is that we don't allow repetition. So this time, once we've taken a letter out of the bag, we can't put it back. So this is going to be more like a factorial case now. So here we're saying how many ways can we select 5 people from 16? So this time we're not choosing all 16 people, we're just choosing a smaller group from that, but we'll see it still has to do with factorials when there's no repetition. So again, let's work with our grid. We want 5 people, so we've got 5 spaces on our grid. And in the first spot, I could choose any of the 16 people. But once I've chosen that person, there's only 15 left, and then 14 left, and then 13 left, and then 12 left. So my solution is 16 times 15 times 14 times 13 times 12 to get my group of 5 from 16. Doesn't look like a factorial yet, and that's what we need to build to. So this is how we can make it a factorial. I can see it's going down by 1. It's 16, 15, 14, 13, 12. But to get a factorial, I have to get all the way to 1. So the way I can fix that is I can add the 11 missing pieces top and bottom of a fraction, because then that's really multiplying by 1. So why stop at 12 when I could do 11, 10, 9, 8, 7, all the way down to 1? But I have to do that to the denominator of a fraction as well to really be multiplying by 1. So what this ends up being, if you look carefully, it's going from 16 to 12 and then 11 to 1. That's really running all the way to 1 on the top. So that's actually 16 factorial on the top and 11 factorial on the bottom. There's our factorials. And if you think carefully about that number 11 on the bottom, that is 16 take away 5. There's 16 people in total and the 5 people I wanted. And that's going to become important shortly. And here's the shortly. The new definition, a new word, permutations. So this is now where we're saying we don't want to take every single piece. We just want to take a selection from a larger group. We may take them all, but now it's becoming more of a broader definition that we might only be taking a smaller selection from the big group. Okay, so a permutation is an ordered arrangement of objects chosen from the set without repetition. And that's where these factorials are coming in. And if we want R letters, say, from a set of n letters, or R objects from a larger set of n objects, then we're introducing this new notation, P for permutation. So the n is the total set, the big set, and R is the smaller subset of that we're taking. And the number of ways that we can choose those things from n things is n factorial over n minus R factorial. So in our case that we just had 16 people and we wanted 5, the n would be 16 and the R would be 5. And that's why we got 11 factorial on the bottom, because it was 16 take away 5. So as a simple example here, how many ways can we form 8-letter words from the alphabet if repetition's not allowed? Well, this perfectly fits the definition of a permutation. There's 26 letters in the alphabet and we want 8 of them. So we would the notation here, we would read this as 26p8, and it is 26 factorial over 26 minus 8 factorial, or 26 factorial over 18 factorial. Now we don't have to simplify that down anymore, actually type it into a calculator or anything like that. It's going to be quite a big number. We're perfectly happy to leave it in this form. Okay, now here is the proof of this formula, and it's a fairly simple proof, and it's pretty much just a more general version of what we did with the 16 and 5 people, but we're using symbols. So we can write npk as n times n minus 1 times n minus 2, all the way down to n minus k plus 1. And that was that 12th term that we got to, if you remember, when we stopped. And then, as we said, we can multiply top and bottom by the remaining pieces to get down to 1. So we end up with that n factorial on the top and n minus k factorial on the bottom. Okay, now this is, as I say there, an examinable proof. You do need to know how to reproduce this in an exam, and it's only a few lines of working out. The most important bit is you need to sit and try and think, and maybe it's easier to see from that 5 people from 16 or the 8 letters from the 26 in the alphabet. Why does the product run from n to n minus k plus 1? That's the key thing that you need to be able to explain. How many pieces are there here and why does it stop at n minus k plus 1? If you can explain that to yourself, then you can do the rest of this proof. No problems, because you just got to multiply top and bottom by the remaining pieces to get the nice n factorial on the top. Okay, now many problems have restrictions in them. And I'm saying here, we always need to deal with restrictions first. We need to get rid of those restrictions before we can start to generalize to the rest of the problem. So I'll do a few examples here and I'll build them up in complexity so that we can see how they work. So in the first question, we want to know how many 5-letter words can we form from changes if A must go first. Okay, so again, we could form a grid here with 5 pieces. A has to be the first piece. And then if you look at the word changes, that would leave 1, 2, 3, 4, 5, 6 letters left to choose from to fill the remaining 4 spots. Okay, which is what I say here. So A has to go first. There's only 4 letters left to choose to make a 5-letter word, because we have to have A in it, and that's out of the possible 6. So that's where the 6 factorial over 6 minus 4 factorial came from. We've got 6 letters to choose from, we only want 4. And that's 6 factorial over 2 factorial. Building up in complexity a little bit, we want to know how many 4-letter words we could form from Nemea if the last letter must be a vowel. So this time it's not a specific letter that has to go on the end. It could be any one of O, U, E, or A. There's 4 of them. So any one of those 4 could be the last letter. And then we've got a remaining 1, 2, 3, 4, 5 letters to choose from, because we're only taking one vowel, so the others are still there. So 5 letters left to choose from, and we'll need 3 of them. Okay, so again, that's where the 5 factorial over 5 minus 3 factorial came from. I want 3 letters out of a possible 5, but there were 4 possible vowels that could have been on the end. It could have been an O on the end, and we solved the problem, but it could have been a U, it could have been an E, or it could have been an A. It could have been any 4 of those, and that's where that times 4 came from. Okay, now another problem. Quite a wordy problem, and unfortunately often these combinatorics problems are quite wordy. 8 people form 2 equally sized queues. So there are 8 people, there are obviously going to be 2 queues of 4. And I'm saying here now, some are more fussy than others. So for instance, Albert will only stand in the left queue, and Beth will only stand in the right queue. Charles and Diana aren't particularly fussy about which queue they're in, but they do insist that they both be in the same queue. Okay, so they don't care if they're in the left and the right, but wherever Charles is, Diana has to be. Wherever Diana is, Charles has to be. Okay, so how are we going to solve this? Well, we know for a fact Albert has to be in the left queue. The left queue has 4 spots. Albert has to be one of those spots. And similarly, on the right queue, there's 4 spots. Beth has to be in one of those spots. We then take Charles and Diana and pop them into, once we choose where Charles is going to be, for instance, is he going to be in the left queue? Then there's only 2 more spots that Diana could be in. Similarly, if he was in the right queue, and then there's some remaining spots to deal with. Okay, so that's what I've said here. Albert can go in any one of the 4 positions on the left. Beth can go in any 4 of the positions on the right. Charles can be placed in any of the 6 remaining positions. Because remember, once we've chosen those 2, there's still 6 spots in the queue, and Charles doesn't care which queue he's in, so there's 6 spots in total he could be in. And then Diana must take one of the 2 remaining spots in the queue that Charles is in. And then once we've done that, that's 4 people chosen. There's still 4 unfilled spots, so they could be done in 4 factorial ways. So in total, it's 4 times 4 times 6 times 2 times 4 factorial, which is 4,608. You've now got more than enough information to work through the exercise, and I'll post that exercise on Google Classroom.